title is Tom's, not mine. State of the art in data fusion, an intimidating title. I'll talk about data fusion as I know it with a few examples, maybe not state of the art. I found this, while thinking about data fusion, I found this image on the website from a company called Trove. And they specialize in data fusion, and they have this thing where they have a lot of inputs, demographic input, premises data, behavioral and social data, news and weather, mobile data, GIS data. All of this data goes into this kind of soup here, and out at the bottom you get data, insights, and action. Right? If only it were that easy. Data fusion doesn't look like that in normal circumstances. What does data fusion mean? Well, the idea is that you have multiple sources of information for the same kind of phenomenon. So maybe it's remote sensing data, and typically these are raster data, they're gridded. Or we have census data or survey data. Typically there are administrative units, there are political boundaries, nations, states, province, municipios, and so on. Some people use expert maps, so the CG centers, for example, often produce these potato maps or other expert maps that can be used. YASA, as you heard, is using crowdsourcing data, where you have maybe pictures or people validating high-resolution remote sensing images. These could be maps, pictures, or point data. And then finally, you may have other kinds of ancillary data. These are not necessarily directly observing the phenomenon, but they are proxies. So maybe climate or soils or slopes may tell you something. Maybe on a south-facing slope, you're more likely to crop, and not on a north-facing slope. You could potentially use that kind of information. It could be about river networks, roads, and so on. These could be in multiple formats. They might be vector data, they might be shapefiles, they might be raster, anyway. So how can we blend these kinds of information? This is my own definition of data fusion. It's essentially to use different sources of information to ultimately hope, maybe should use the word hope to create a better product than any one of the individual products alone. There are different kinds of approaches, or you may think of as different philosophies in using this. The one approach that most people talk about is disaggregation, where you start with some kind of information like an FAO data or subnational statistics, and you believe that's the truth. And what you want is better spatial information. So you start with that and you try to figure out some way of disaggregating that data. But you can imagine another approach where you trust the raster data, the remote sensing data. The remote sensing community will tell you that their observations are, as good as direct measurements, so why bother looking at the census data? But the other argument is the satellites are, many kilometers up in space, so they cannot really observe what's on the ground very well. So another way of thinking about it is, okay, maybe you trust the remote sensing data, but then you refine that kind of raster data, bringing in other kinds of ancillary products. Define raster. Raster means gridded. Essentially, you divide the world into different little boxes, and each box has a particular value. Versus a pixel, exactly. Vector data or administrative data or polygons, like you look at our FAO data where you have different countries, and each country or each subnational state or province has a value. Another approach could be a hybrid approach, and this may be similar to what SPAM is doing, and I think not many people have explored this very carefully, where you don't trust any of them. You're kind of agnostic to which data is better, and you try to build a model that tries to get the best guess that fits between all of these different sources of information. SPAM is something like that, but I think you do more disaggregation. A few years ago, I met somebody at the University of California, Santa Barbara, who's a statistician, and he was developing models where not only could he predict the median estimate, but he could also come up with models that predict both the minimum and the maximum estimate between different sources of information. So I think with those kinds of tools, we could build in uncertainty like Jerry Nelson was asking for yesterday, and develop models that not only predict a mean, but kind of the distribution of probabilities of different variables. Just to give you some examples of how this is done today, these are purely examples. I don't necessarily think of them as state-of-the-art. The ILRI, there's a huge consortium of ILRI, FAO, Oxford, and other groups that have developed a global livestock map that Peter talked about or mentioned. What they have done is to start with subnational livestock headcount data. So they have the best available census survey kind of data of livestock numbers, and then they disaggregate it using climate data. Okay, so they use climate, temperature, and rainfall as a proxy. They build models relating those two. So first of all, you can ask whether that's a good proxy or not. That's one question. But secondly, you should note that these gridded climate data themselves are actually models. Okay, so they're models of models. The gridded climate data are interpolated between climate station records. So this may be fine, but if you want to trace the lineage of the data, this is what you need to do, is to figure out where all of these data sources come from. The other example is from ILSI. I don't need to go into too much details because Peter talked about it. You can talk about two different efforts from ILSI. The first one is where they blended different remote sensing data to create what they call a hybrid remote sensing product. So they said we don't necessarily believe MODIS or GLC 2000. So they took 4 different remote sensing maps and then they built confidence maps, saying if three maps agree, then we have more confidence than if that this pixel is cropland, than if only one of the maps agree. So they're rule based, but they're bringing different remote sensing products from different dates. So some of them are from 2000, some of them from 2005, and so on. Then what they do is they use these rules to disaggregate census data. So you start with some census data and you use these rules to say we have high confidence this pixel is cropland, so we're going to give most of the cropland there first, and then disaggregate it that way. They are also working on some other approaches now, along with FAO, where they had a workshop where they brought in regional experts bringing in their own regional maps. So somebody from India brings their best regional maps. So they're taking these kinds of national products, developing some rules to look at quality of these products, and then kind of slapping them together to develop a global product. So I believe FAO and ILSI are working on this right now. And they're now also using the crowdsourcing data to provide information for validation or quality control of these global products. The last example I'm going to give you is the work that we've been doing with Geoshare to create a global cropland map. I should acknowledge my colleague, Dr. Danny Plouffe, who essentially did all the intellectual heavy lifting on this work. I was hoping to officially release the Geoshare cropland data at this workshop, but we have some bugs. So it's not an official release yet. So you've seen a poster last night. If you haven't, I'll quickly go through this. Our approach is essentially to blend remote sensing data and census data. In the most recent version, we are using cropland probabilities. I'll tell you in a second why. At 500-meter resolution from MODIS satellite. So 500-meter resolution, that's about something like 80,000 pixels by 40,000 pixels in latitude by longitude. And we have administrative unit data for roughly 40,000 administrative units around the world. We blend them to ultimately come up with a cropland map for 2005. That's at 2-kilometer resolution. Our older data were at 10-kilometer resolution. So it's about 5 times finer. Why do we use probabilities? Well, in our previous work, we were using the land cover classes themselves from the MODIS satellite data. So this shows 2 different land cover classes. Shows croplands in the dark brown and then mosaics in the kind of orangish color. This is a zoom into the Pampas region in Argentina. This is what the census data says for that same region. And what we found is that we were never able to get this kind of nice C shape in the census data in Argentina when we just used the land cover categories. Part of the reason is because when a MODIS satellite, even though it's fairly high resolution, it's still classifying each pixel based on its dominant land cover class. So if the dominant class is cropland, it calls it cropland, even if that percentage of cropland might be 30%. If all the other land cover classes are less than 30%, that's the dominant class, right? So what we found is that in fact, if you looked at the classification scheme uses underlying it, actually uses probabilities. It's building a model to look at the probability of each class, and then it picks the dominant one. But the underlying probability surfaces are there, which is not publicly released. So we work with the people at Boston University to get the underlying probabilities, and once we look at the underlying probability surfaces, you get a much better characterization of cropland in these regions. Right? So we are working with these probability surfaces, and so for different land cover classes, you have different probabilities of cropland, and the probabilities don't actually translate directly to density of cropland or the extent of cropland in a pixel. So what we are doing is we are bringing in the census data now to say what is the best function that fits the probability, that translates probability into density to best match the census data across different regions of the world. Okay, so this is our fitted function for North America. Sorry. This is our fitted function for North America for 2 different land cover classes. This is for Southeast Asia. So they're different for different parts of the world. Once we do that, you can then say this is what our model fit looks like for North America. So this is the cropland from the census. This is our cropland that we calculated. So we are fitting a regression model. It doesn't exactly match the census, but it's a regression across all of North America. So the points lie on a roughly around a 1:1 line. And then you can apply those functions in different parts of the world to develop a map like this. I call this version 1. I'll tell you why in a second. So this shows cropland density from 0 to 100% across different regions of the world. This is comparing the older version from year 2000 to the new 2005 version. We went from 10 kilometers to 2 kilometers. Instead of land cover classes, we are using probabilities. And we have roughly tripled the number of administrative units. Okay, so why version 1? Version 1 is doesn't exactly match the census data, so it's based on a model fit, right? But what a lot of people have done in the past is say we can't really use your data because it doesn't match FAO or it doesn't match the census data. So we are now developing 2 different versions. This is horses for courses. Maybe in your economic model you cannot use a data set unless it matches FAO. So we are doing a version 2 where the data is scaled to match the census data, and the scaling in this case is probability dependent, so higher probability cropland is scaled more than the lower values. Anyway, that's a detail. And then we are developing a 3rd version where it's scaled to match the FAO data. And so this is an example of what a version 1 for South America looks like compared to a version 2. So you can see some differences where once we scale it to match the census data, some of these features change a little bit. Anyway, so your horses for courses, in some sense, both of them are equally valid. This one matches the census data, this one matches the remote sensing data better. So when we release this data, we plan to release 3 different versions. And version 1 can be thought of as being one that's more true to the remote sensing data, but the remote sensing data is now refined and calibrated to the census data. Version 2 trusts the census data, but it could be thought of as a disaggregated product. And version 3 is something that could be thought of as a disaggregated FAO data set. So one question that comes up all the time is like, it's 2014, why the heck are we still in 2005, right? We should be working on 2010 or even maybe 2012 or 13. First of all, censuses, we rely on census data for this kind of work. And censuses, even in the best case, are done every 5 years. In the worst case, some censuses were last done in the 70s in some countries in Africa. So we rely on these censuses. Second, even if the censuses are conducted a few years ago, they take a couple of years to get published. They need to be quality control, so a 2012 census may not be published until 2014 or 15. So we still don't have circa 2010 censuses for many parts of the world. So this is a challenge. Secondly, these kinds of one-off efforts take time. So I have this product had a master's student working on it full-time for more than a year. So it takes a year roughly to pull all the data together, quality control, look at the definitions, match the data, the tabular data to administrative boundaries, which are changing all the time, and so on. You need to find the personnel to hire them. The data needs to be compiled, a lot of complications there. Matching funding cycles to people. Sometimes you have the right people, you don't have the money. Sometimes you have the money, you don't have the right people. This is always a challenge. So sometimes it takes a year, 6 months to a year to get a project going. In academia, we also have the academic cycle. Students come in during the fall, and if you're past that cycle, you have to wait till the next fall. Anyway, that's all I have. Hope I have time for questions. Thank you.